So if you've already made your legend and you've chosen 4 different colors, here is our unit circle. So a reminder of what our unit circle is. It's a circle. Its center is right at 0, 0, and it has a radius of 1 unit. That's why it's called a unit circle. So what we're going to do today is we're going to develop certain angles on our unit circle that you're going to need to know the coordinates on the unit circle, be able to figure out sine and cosine, and these will all be ones that you're going to be able to do without a calculator. So our job is to be able to calculate some mathematics with sine, cosine, and tangent without our calculator with a bunch of special angles. And we find out that it's actually quite easy if we use some of the big ideas that we've learned already. So on the legend, in addition to color coding things, the degrees in blue, radians in green, and so on, we've got 2 of our big ideas showing up. One of our big ideas that we listed before was any coordinate on our unit circle, instead of being listed just as their x and the y coordinate, those x and y coordinates also mean cos of the angle theta and sine of the angle theta. That was one of our big ideas. And another of our big ideas was that tan of any angle was equal to sine over cos. So our unit circle is going to be split up into a bunch of different angles, and we can categorize those angles by families. And the first family that we're going to do is the axes family. So when we're looking at the axes family, we're looking at the coordinates on the unit circle that run into the axes. So those are the points that are part of the axes family. We're going to start with degrees because that's our easiest thing. If you started at this first point, everybody be fine with that as being 0 degrees in standard position. If I went to this point at the top, that would be 90 degrees. And so we're just going to label. We're not going to draw the little arrow thing showing it's in standard position because then this is going to get too busy and too messy. That one's 180. What's the next axis? This one, 270. And you could put with 0, it could also be 360 degrees. And we're just going to go once around. We could do coterminal angles and keep going, but we'll just go once around with degrees. So now we have to think, what are these also in radians? Well, 0 degrees would also be 0 radians. Which one do you want to do next? We don't have to do them in order. 90 degrees, we can do them in order. 90 degrees is pi over 2, or 1.57 radians. Because 180 is pi radians. 270 is 3 pi over 2, and we went all the way around. 360 is also 2 pi. So we've used our axes and labeling them in radians already to help us figure out where an angle would be. So we did, I think we did a question that was negative 12 pi over 11. And we had to figure out, well, 12 over 11 was a little bit more than 1. So that helped us by labeling our axes to figure out what quadrant that was in. Now this is where your unit circle becomes really powerful, because these first 4 coordinates, if you know that the center of the circle is 0, 0, and you know that your radius is 1, what are the coordinates of this point? What would the x coordinate be? What would the y coordinate be? 1, 0. Because you've gone 1 to the right, but haven't gone up any. And here, the coordinates of this point? 0, 1. Now we're getting into negatives, so this will be negative 1, 0, and 0, negative 1. And this is where I start getting excited about things, because that was pretty easy to label those points. But do you realize how powerful that is? In that I can now ask you mental math questions like, what is sine of 90 degrees? The answer's up there. What is sine of 90 degrees? It's 1. Okay, Shammy, pick another volunteer. What is cos of pi radians? -1. Excellent. What is sine of 270 degrees? Close. -1. So how did they get that? How did they see those answers? Because probably before today you never did those mental math things of like sine of 270 degrees or figuring out that cos of 2 pi is equal to 1. But the answer is in one of our big ideas, right? One of our big ideas is that our coordinates are always cos comma sine. So when I look at this coordinate up here, 0, 1, that means cos of 90 degrees is 0. It means cos of pi over 2 is 0. When the y-coordinate is 1 on the unit circle, that means sine of 90 degrees is 1. Sine of pi over 2 is 1. Our y-coordinate on the unit circle always represents sine of that angle. Our x-coordinate always represents cos of that angle. And now we can also use our big idea with tan and our coordinate to figure out what tan is. So if I want to, and I'm going to write this, when I do tan, each time I'm going to write tan, and I'm going to write the angle, and I'm going to choose in radians. So tan of 0, well, tan is sine over cos. So tan will be the y-coordinate, which is 0, over the x-coordinate, which is 1. And if I do the fraction 0 over 1, I get tan of 0 will be 0. When I go up to pi over 2, tan of pi over 2 is, well, 1 divided by 0. What happens when you do 1 divided by 0? It gets undefined. So we can write undefined because that one is not possible. You can't have tan of pi over 2. If you try it in your calculator, if you try tan of 90 degrees, your calculator is going to tell you an error. When I get to tan of pi, (0 over -1), that will be 0. And tan of 3 pi over 2 will be undefined again. So just because you can label those points, and they're really easy to label because your radius is 1 and they're right on the axes, you now know sine, cos, and tan for those 4 angles. And by labeling your unit circle, you can now do those things without having to use your calculator. Now on your piece of paper, in between the 1 and the 2, you've got a little bit of space right here. So what I would like you to do in that space, I'm going to sort of model it right here. What we're going to write is we're going to write special triangle for 45 degrees. And 45 degrees in radians is pi over 4. And so we're now going to look at the pi over 4 family. The pi over 4 family on your unit circle is all the angles on your unit circle that have a reference angle of 45 degrees. Can you see that all 4 of those lines there, all 4 of those angles would have a reference angle of 45 degrees? The reference angle being the angle back to the nearest x-axis. And so our special triangle for a 45 degree, since we want to figure out what sine, cos, and tan are, because then we're going to be able to label the coordinates of these points, we need to draw a right angle triangle with one angle being 45 degrees. If I do that, what's the other angle? 45 again. What's special about that triangle? It's a right angle triangle, and what else is it? What other kind of triangle is it? Not equilateral, because not all the sides are the same. It's an isosceles triangle. What are the properties of an isosceles triangle? You have those two angles the same, and two sides are the same. So we know that this side and this side are the same. And the powerful thing about sine, cos, and tangent is sine, cos, and tangent are ratios of sides. It's not, you know this, you know that sine is the opposite over hypotenuse. It doesn't matter how big or how small I make this triangle, the opposite side divided by the hypotenuse will always be the same. So by having this triangle, what I can do is I can pick any number I want for my sides here. I could pick 1, I could pick 2. If I really want to put myself through some painful mental math, I can pick 1,482. I'm not going to do that. But if I chose 1 here, I have to choose 1 there. If I chose 2 on one, I had to choose 2 on the other. And if you do a squared plus b squared equals c squared, you will get the square root of 2 as your hypotenuse. So because we can do that, because it's a special triangle, and because the sine ratio doesn't change no matter how big or how small, cos ratio doesn't change no matter how big or how small, we can pick some values for one side, and now I can say, I know what sine of 45 degrees is. Sine of 45 degrees is, I'm just going to move that over a little bit. Sine of 45 degrees is the opposite over hypotenuse. It's going to be 1 over root 2. And if I would rationalize the denominator by multiplying top and bottom by root 2, you would get square root of 2 over 2. And on my unit circle, I'm going to label them rationalized like that. It wouldn't be wrong if you wrote 1 over root 2, but I'm going to write it as root 2 over 2. Can you see that cos of 45 degrees, wow, there's an S in there, is also the same, 1 over root 2 or root 2 over 2. And what's tan of 45 degrees? Opposite over adjacent, 1 over 1, so it's just going to be 1. So by having that special triangle, the idea is, can you see that that special triangle happens right here with this reference angle? It happens, don't draw these in, it happens again there, it happens again, that same one with reference angle. All of them happen in all of those places. Those triangles are all that special triangle happening over and over again. So before we label our coordinates, let's start again color coding things. I had chosen blue for degrees. Since this is our 45 degree family, in quadrant 1, that's going to be 45 degrees. What is the family member in quadrant 2 that has a 135 has a reference angle of 45? What would it be in quadrant 3? $225. And quadrant 4? $315 degrees. That was pretty good. Your mind for degrees works well. Now we're going to go to radians, which your mind hasn't been worked as much. This is going to be pi over 4. What are you going to find in quadrant 2? Well, how would you find it? If this reference angle is pi over 4, how did you find 135? What did you do to figure out 135? You went 180 and you subtracted 45, right? So now we have to do the same thing in radians. So how do I do this? It's going to be 3 pi over 4, you have to use your fraction skills. How do I subtract fractions? I need a common denominator. Do I have a common denominator right now when I'm subtracting those? No, one's over 1, the other one's over 4. So if I change the pi to 4 pi over 4, 4 pi over 4 minus 1 pi over 4, does it make sense that you would get 3 pi over 4? What are you going to get here? Quadrant 3. Well, what would you do in degrees? You did 180 plus your reference angle, right? So now we have to do pi plus pi over 4. Now we're adding fractions. I need a common denominator. It's over 1, so if I multiply top and bottom by 4, I get 5 pi over 4. And finally, in quadrant 4, it's going to be 7 pi over 4. Because you're going to think, well, I'm going to have to do 2 pi minus my reference angle. And again, I need to have a common denominator to do that. So I need to change 2 pi to 8 pi over 4. You are going to change 2 pi to all sorts of fractions over all sorts of different numbers because you're going to have to get used to working with different reference angles. And so radians works a lot with fractions. So now that we've labeled all of our degrees and all of our angles and we've made our special triangle, we can now say exactly what is the coordinates here. Well, using our big idea, the x-coordinate is cos of theta. The y-coordinate is sine of theta. So if I would do that, cos of 45 is root 2 over 2. And sine of 45 is root 2 over 2. And the coordinates of that point on the unit circle are exactly that. When you have an angle of 45 degrees and it hits the unit circle, it will hit it at the coordinates root 2 over 2, comma root 2 over 2. Now, I think I mentioned yesterday, you're going to have this, all of these values memorized. And there's a lot of them on there. But you're going to notice some patterns, because once you get into the pi over 4 or 45 degree family, since you know that coordinate, you're going to know this coordinate. Negative root 2 over 2, root 2 over 2. Well, the x-coordinate in quadrant 2, all your x-coordinates are negative there. That makes sense. Your y-coordinate's going to be positive. And since it makes the same special triangle, you're going to have the same values for sine and cos. But the other thing that comes up is because it's in quadrant 2 and your x-coordinate's always negative in quadrant 2, the cast rule appears. Because you know that your x-coordinate is cos, and cos is always negative in quadrant 2, it makes sense. And in quadrant 3, what about sine and cos in quadrant 3? They're both negative. And in quadrant 4, the x value would be positive, and the y value would be negative. So we can do some mental math again. Where did we end up? Who was the last person to answer? You can pick someone for sine of 135 degrees. Oh yeah, Bianca. Root 2 over 2, perfect. How about cos of 7 pi over 4? Ray's already gone. Close. Cos of 7 pi over 4. Remember, which is your cos is your x or your y? your x. So then we go 7 pi over 4, you look at your x coordinate, root 2 over 2. How about sine of 5 pi over 4? We figured that out from the special triangle. So once I drew this special triangle, and I took this angle of 45 degrees, and sine is opposite over hypotenuse, I wrote 1 over root 2. I rationalized the denominator here by multiplying root 2 on the top and root 2 on the bottom. And so then that becomes root 2 over 2. So if you didn't know this, then we wouldn't be able to label this unit circle right now. And there's going to be some angles that we won't be able to do with our without our calculator, like 40 degrees, because we can't make a nice special triangle with 40 degrees. What we're going to do is we're going to develop the 45-degree family. Next, we're going to do 30 and 60. Later on, we do all the angles that include 15 degrees. And over time, mathematicians have figured out ways to figure out other ones without your calculator. Okay? Now we have calculators now, so the advantages of this were way more important when there wasn't calculators, which makes sense, because if you had to figure something out a long way or measure it, it wasn't very accurate. As soon as they could figure out things mathematically, it went faster. And so they developed a whole bunch of mathematics that allowed us to figure out these things. Developing this mathematics helped them make other discoveries in other areas, so it really expanded mathematics in a lot of ways. So what we do right now is we're learning which ones could we do without our calculator. How would we figure those out? And when you do math contests and certain things without your calculator, or even if you're allowed your calculator, certain angles, if you can do them quickly in your head, they make the math a little bit easier. So the last thing we need to add to this one, the only thing we haven't done, is our tan. So tan of pi over 4, well, if we look at our special triangle, tan of 45 degrees is 1. When we go to quadrant 2, it's going to be -1. Can you see that if tan is sine over cos, if you do root 2 over 2 divided by root 2 over 2, you're going to get 1? Yeah. And in quadrant 2, one of them's positive, one of them's negative. You're going to get a negative. In quadrant 3, they're both negative, so when you do tan of 5 pi over 4, you get positive 1. And tan of 7 pi over 4 is -1 again. It's just the cast rule, but it's also now connected to our big idea, right? Because our big idea says that tan, one of our big ideas is tan is the sine divided by cos, which is the y-coordinate divided by the x-coordinate. And if they're the same, you're going to get 1. But if one of them is negative and one of them is positive, it's going to be a -1. And it matches with our cast rule, because tan is positive in 1 and 3 and negative in 2 and 4. For the 30-degree and the 60-degree triangle, there is one special triangle that does both of them. So we're going to, in this little space in here, we're going to draw our special triangle for 30 degrees and 60 degrees. And the reason why it's a special triangle for both of them is that if I draw a right-angled triangle, and we have to draw a right-angled triangle in order to do sine, cos, and tan from SOHCAHTOA, and I label one angle as 60 degrees, what does the other angle have to be? 30 degrees. So it makes sense that if this was a special triangle for 30, it's also a special triangle for 60. It is pi over 3. The negative is just photocopy from this paper. It's not actually there. I will add some white out. Okay. It's really whited out. Okay. No, it's just pi over 3. This is a right triangle. What is the other name of this triangle? Is it isosceles? No. Someone said it? Scalene. What does scalene mean for a triangle? It means it's not special at all. They gave it a nice fancy name so it can maybe feel special, but equilateral triangles had all the sides the same. Isosceles, 2 sides the same, 2 angles the same. So all these triangles felt important. All the other triangles felt left out, were not special at all. So they gave them this scaly name, scalene, to maybe make them feel better, but no. It's just a special name to say you're not special. What can you tell about a scalene triangle? Nothing. Other than, a squared plus b squared equals c squared, but that works for all right-angled triangles. So there's really no help for this one. But this scalene triangle, well, all of a sudden ran into a scalene triangle exactly the same, and they got together, and then they realized, together we're special. And so if I draw another triangle identical to this one, and I make this 90 again, I make this 30 again, if these two triangles come together, and now, why are they special now? Because it makes an equilateral triangle. So when we put a 30-60 triangle together with another 30-60 triangle together, it makes it an equilateral triangle. And what do we know about an equilateral triangle? All the sides are equal. So again, just like last time, you can pick any number you want. We could pick 3.9 for all the sides, but that's not going to make our math really easy. Sometimes when we're picking random values for sides, we do want to choose numbers that make most of our math easy. In this case, can you see that picking 2 for a side is really nice, because then on the bottom, I can break it up to be 1 on here and 1 on there. Because they're going to be the same length, because they're identical, and if they have to add up to 2, then they both have to be 1. Can you see that you can now do a squared plus b squared equals c squared to find the height? So a squared plus b squared equals c squared, we can find out that this length is root 3. And these were values that you memorized last year, but we're going to write them out again. So we'll do 30 degrees first. Sine of 30 degrees. Opposite over hypotenuse. 1 over 2. Cos of 30 degrees. Adjacent over hypotenuse, root 3 over 2. And tan of 30 degrees, opposite over adjacent, 1 over root 3. We are going to rationalize this and write it as root 3 over 3. We can also do sine, cos, and tan of 60 degrees. Sine of 60 degrees, opposite over hypotenuse, cos of 60 degrees, and tan of 60 degrees, opposite over adjacent. So this special triangle, by being able to draw it and recognizing that if 2 of them came together, it would make an equilateral triangle, allows us to choose values and put them on there. Just so that you can see let's say you picked a different value. And I'm going to only show this for 30 degrees. And you'll have to take my word that it's going to work for 60 and it's going to work for sine, cos, and tan. But pick a not nice number, any one you want. 41. So if I chose 41 for this side, that would be 41 for this side. That would make each of these 20.5. Awesome. Okay. A squared plus b squared equals c squared. In your head, you're going to get 41 root 3 over 2. Yeah. Yes, I think so. Good. Right? If you simplify it when you... Oh, but what's sine of 30 degrees? 20.5 over 41. What does that simplify to? 1/2. Doesn't matter what numbers you chose. If you took it and you simplified it, you'd get 1/2. Okay? If you took, I'll do it for one more, tan of 60 degrees, you get 41 root 3 over 2 divided by 20.5, which this is really 20.5 root 3 over 20.5, which would simplify out, and you would just get root 3. They're the same. It doesn't matter how big or how small. Like this is what makes trigonometry so powerful. And hopefully they keep teaching you this year after year, that it doesn't matter how big or how small. The ratios stay the same. So if you forget, you can draw your special triangle. If you forget which values you need to choose on there, it doesn't matter. You could have chosen 41. It just makes some of your math, like doing a squared plus b squared equals c squared, is not very much fun to get 41 root 3 over 2. I cheated a little bit because I knew it would work out to that. But it doesn't matter. And so now that we have this special triangle, we can go back and we can start with our 30-degree family, our pi over 6. We can label our dots where our coordinates are going to be. We can start with our degrees and then go to our radians. And I'll give you a 10-second head start. And your job is to see if you can finish labeling all your degree angles before I do. And then I'll give you another 10 seconds after that. And you have to see if you can finish all of your radian angles before I do. How did you do with degrees? Did I beat you? Yes? So what did you have to do? Well, this one in quadrant 2, you'd have to do 180 minus 30 to get 150. Quadrant 3, 180 plus 30. They all have a reference angle of 30. In quadrant 4, 360 minus 30. You want 20 seconds for the radians? Okay. How did you do? So we got 5 pi over 6, 7 pi over 6, and 11 pi over 6.
Yeah, that's what I thought too.
What's that?
I thought it said 16, not 6.
Oh, yeah, this one looks slanted. Yeah, I'll try and make that look more like pi over 6, not 16 on the bottom. And so you did the same thing here in quadrant 2. You would have to do pi minus pi over 6, but you need a common denominator. So pi is the same as 6 pi over 6. You subtract 1, you add 1. So sometimes what people do is they just sort of recognize that pattern that this is always going to be 1 less than the denominator, because you'd have 6 pi over 6 minus 1. And this one's going to always be 1 more than the denominator, because you have 6 pi over 6 plus 1. And that happened, did you see that that happened in this one as well? 1 minus the denominator here, 1 plus the denominator there. Kind of cool. Little things that can help us memorize them. And so now we're going to do coordinates. Remember, our x coordinate is cos. So if we do look at our special triangle and say, what's cos of 30 degrees? Root 3 over 2. Sine is a half. I'm only going to give you 5 seconds for the coordinates head start. So there are your coordinates. Again, they follow the cast rule, which follows naturally where x coordinates and y coordinates are positive and where they're negative. And finally, we can figure out what tan of each of these ones are. Tan of pi over 6, root 3 over 3. So are you starting to notice that if you know what happens in quadrant 1, you know what happens to the coordinates and tan in all of the other quadrants? And that's why reference angles are so powerful. Because no matter which one of those angles you choose, if you drew a line back to the nearest x-axis, you would create the same looking triangle every single time. So your coordinates for sine and cos are going to stay the same. Can I click to the next one? We ready? And so finally, our last family has to do with these coordinates on the unit circle, where all the reference angles are 60 degrees. Or pi over 3. How are you doing? 10 seconds again for the degrees. Is that going to be enough? Here we go. Do a check. How did you do? And 20 seconds for the radians. Oh, don't make it look like 13. Pi over 3. Two pi over 3, 4 pi over 3, 5 pi over 3. The pi over 3s I kind of find, since they make the pieces all the same size, it kind of makes sense that this is 1 pi over 3, this is 2 pi over 3s. The next piece would be 3 pi over 3s, which is just pi. 4 pi over 3, 5 pi over 3, and then 6 pi over 3s, which is just 2 pi. You can't quite do that with pi over 6s because there's pieces missing, right? This would be 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6, 7 pi over 6, 8, 9, 10, 11, 12. But maybe that proportional thinking also helps you figure out what the angles are. Because we have to memorize all of our radians, all of our degrees, and you'll want to have some nice strategies to figure that out. So this counting strategy is one of them. I mean, it works for pi over 4 as well. 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, 8 pi over 4. But maybe you're starting to notice that other pattern I mentioned. This one's 1 less than the denominator. This one's 1 more. This one's always double minus 1. Because that's how you would have done it every time with your reference angles. Sure enough, does it work for this one? 1 less, 1 more, double minus 1. Yes. Here, 1 less, 1 more, double minus 1. Double the denominator, then subtract 1 to get your numerator. Because that's what you do when you do your reference angle, right? How do I get a common denominator? I have to get that to be 6 pi over 3, which is always double the denominator, and then you're subtracting 1. Coordinates. Looking at your coordinates, cos of 60 degrees was 1/2. Sine of 60 degrees was root 3 over 2. 5-second head start on your coordinates. Yes. I got the 1/2 and the 3 over 2 back from my special triangle. So there's my special triangle. And remember that your x-coordinate is cos. So for 60 degrees, I went cos of 60 degrees is 1/2. And sine of 60 degrees is root 3 over 2. That's going to be my y-coordinate. And finally, tan. There are all your tan values. So notice for the families, the values stay the same. Just positives and negatives change according to the cast rule, which change naturally according to where x coordinates are negative and y coordinates are negative. And there we have all of our unit circle. So putting those all together on one thing would be all of your values. And on Friday, you are going to have a quiz on all of those. So it is the only quiz during the year that I give you before the quiz. Identical.